Hello students, so today we are going to learn the various parameters of an op-amp. So the very first parameter that is there to define the op-amp is the offset voltage. Basically, we require an op-amp that has got a minimum of offset voltage. So this is caused due to the input offset current, bias currents, and input offset voltages. So as I described in my previous lecture also, that when we talk about your op-amps, they are manufactured by using two similar type of BJTs. So basically, when we talk about your BJTs, even if we try to have the same number of two ICs, their characteristics are never same. So here we apply the positive voltage and here we apply the negative one. So this is your input one and input two terminal. So basically, when there is a difference between the HFE and VBE, that is the base to emitter voltage of the transistor, then there will be a difference in the bias currents. Now you all know that biasing is required for the proper functioning of all the transistors. Without biasing, there are different kinds of biasing that is used in BJTs. And when we use these BJTs, because of the fabrication defects that occur during the manufacturing of your op-amps, there is a difference in the bias current, that is IB1 and IB2. To show you in the form of the op-amp, I can just draw like this. So this is my one terminal, this is another, this is my source resistances. So this is my IB1 and this is my IB2. Let's say this is positive and this is negative. So my input offset current, this input offset current given as I of IO, IO stands for input offset current. So that will be equal to the difference between the current at the positive terminal minus the current at the negative terminal. And now because of this current that is flowing through this, there will be a voltage that will be produced in the source resistor, and because of which this offset voltage is generated. Because of this offset voltage is generated. Now in the similar case, we can describe this bias currents. That is the current that is required for proper functioning of these transistors as IB1 plus IB2 divided by 2. So this is the bias current that is required for the proper functioning of the operational amplifier. So now if there is a difference between IB1 and IB2, because of that, again, there will be a rise in the offset voltage because of these bias currents. So there are two types of this differences. First is because we have to provide bias currents for the proper biasing of these two transistors, and because of which there will be a voltage that will be potential that will be there across the resistors through which it is going to flow, and that is going to give rise to the offset voltage, number one. Second is because these two currents IB1 and IB2, because of the difference in HFE and VBE, there will be a difference between two. So because of this small current IIO, there will be again offset voltage generated. So now let's discuss your input offset voltage. Let me rub this. So as I just discussed, let's take a numerical example of this bias offset voltage. So let's say this IB is of the order of 10 nanoamperes and the value of this RS is 1 mega ohms. So now the voltage that will be generated because of this bias current will directly be equal to 1 multiplied by 10 raised to the power 6 multiplied by 10 into nano means 10 raised to power minus 9 volts. And if you just cross verify the answer, you are going to get 10 millivolts as the output voltage. And because of this type of voltage that is there at the output, what you find out is a error in the sensor detection activity. As because of this voltage that has just got generated because of the bias current and the difference between that input by offset bias currents, there will be a misunderstanding that a sensor is sending a voltage that is being measured. So this should be very small as possible. Now we come on to your input offset voltage. Basically, if your both these terminals, positive and negative, are not applied with any input, there is no input, V1 is equals to 0 and V2 is also equals to 0. Ideally, output should be equal to 0. But because of the fabrication errors in the two transistors, there is some output voltage. It is there. So the input offset voltage that is given by VIO, it is given as the minimum amount of voltage that is required at the input terminal to make VO equals to 0. So it should be minimum again as much as possible. So now we switch on to your second parameter, and that is your slew rate. So now we come on to the second parameter, and that is slew rate. So it is the maximum rate of change of an op-amp output voltage. What is the rate at which the op-amp output voltage is changing when we are providing it the input? And how it is measured when 1 volt is applied to the input of the op-amp and the rate of change is measured from 10 to 90% of the output signal. So basically, if you want to just understand it carefully, just see to this diagram that I am just drawing. Let's say that you have applied a square, or you say that you have applied a sinusoidal input. In actual, the op-amp should go according to your this sinusoidal input that you have applied. But if you check out the output, you just take a signal generator and give it a sinusoidal output from this to the CRO. And if you are going to see that how your and give this to the op-amp, and from op-amp again give the output to the CRO. When you are going to match the two, how you are going to getting the output is the output will be equal to just like a triangular wave. Let me draw it a little bit magnified here. Basically, let me draw only one signal. So now you will be able to understand it. So when it is changing, your op-amp cannot follow this change, and it will be just taking it like this. And again, when it is decreasing to 0, it is going to go till here, and again it is going to go till here. So actually you are applying it a sinusoidal wave, but it cannot follow it, and so it provides you a triangular wave like that. So similarly, when you are going to apply to it a step input signal, square waves you are going to provide, what it is going to do is at this time, let me just mark out some lines parallelly to here. So when your this output has reached from 0 to let's say 1 volts, within an instant, your this output will start rising, and it will take some time to rise to 1 volts, and then it will reach its constant value. After that, let me just draw it a little. So how your this amplifier is going to provide you the output? When your this output has changed from 0 to 1, it will take a little bit of time to reach to 0 to 1 and like this. And as soon as it is going down from 1 to 0, it is decreasing, then it will again decrease, but the output will be in the form of this. It will not be a complete square wave, but it will be a little bit of change. And this thing is defined by slew rate. What is being done is, you people will see that if you are going to experiment it in your labs with your signal generator, your op-amp kit, and your CRO, you are going to find that those op-amps are behaving like this. Some can behave a little bit in the better way as compared to other kits. So that is defined by the slew rate, and ideally it should be infinite. That means the output should instantly follow whatever input is being given to it. So now we come on to the third parameter, and that is CMRR, that is defined as common mode rejection ratio. It is the ability of the op-amp to reject the common mode signal. Common mode signal means that when your sensors and transducers, they are working in an industrial environment, there will be a lot of noise there. And your signal that is of the order of millivolts will be embedded in that noise that is being sent as the input to this op-amp. If the CMRR, that ideally should be infinite, of this op-amp, if CMRR is very high, what your this op-amp is going to do, it is only going to take out your this signal, and the common mode signal, that is the noise in these both cases, will be cancelled out. It will be 0. So to define your CMRR, let's say that you have applied a same signal V1 here and some signal V1 here along with the noise there. So you know that your V0 output is equal to gain times the input that you have applied. Let's say in this case, you have applied a common mode input defined as VC. So now your this gain, let's term it as common mode gain. So your this AC will be equal to V0 upon VC. Now we come on to your differential input. Let's say that you have applied V1 here and V2 here. So now your this differential gain multiplied by V1 minus V2 will be the output here, right? So this is the same op-amp to which we have applied it. Now what is going to happen is your this AD again will be equal to V0 upon, let's say, the differential input, right? Your desired signal that we require. So the ratio of your AD to common mode signal will provide you with the value V0 upon VD multiplied by, that will be V0 and VC. So this V0 and V0 cancels out, you get VC upon VD. So now when we talk about CMRR, it is actually your this CMRR, it is actually the ratio of common mode gain to differential gain, the reciprocal of this thing. So that gives you VD to VC, that is the differential signal or the desired signal to the unwanted signal. Desired signal to, because common mode signal is the noise to which we are talking, so I am just writing here the undesired signal. And your undesired signal actually should be equal to 0. That makes that ideally the CMRR should be infinite. The desired signal amplification should be maximum. It should be able to take out this desired signal out of the noise that is being given to the both terminals of the op-amp. So next we come on to drift. Drift means the error signal that is generated because of two things. One is aging of the operational amplifier, and second is because of the temperature effect. We all know that when we talk about your semiconductors, they are highly affected by the temperature variations in the atmosphere. So because of this, there can be an error signal generated in the op amps, and for that purpose, a output voltage gets generated that is called the drift voltage on that. So this should be minimal. Ideally, your this parameter should be minimal. So now we come on to the last parameter, and that is the hysteresis effect that is used in the op amps, and that is required in the Schmidt trigger. Now basically when we talk about Schmidt trigger, it generates the square wave pulses. So it is given like this. It generates the square wave pulses. This is the V naught. And basically what happens is there is two threshold voltages that are defined. One is your lower threshold voltage and other is your upper threshold voltage. Okay. So now this is your output of the operational amplifier. Now what will happen? The signal that you have just got may be consisting of a lot of noise. And how your this Schmidt trigger works is it takes into account the crossing of your this signal when it crosses the upper threshold voltage. Only then it is going to generate a square wave till it crosses the lower threshold voltage. As soon as it crosses the lower threshold voltage, it falls to 0. And as soon as it crosses the upper threshold voltage, it generates a 1 there. So this is how the pulses are generated. Again, when your this noise signal is going to cross your upper threshold voltage limit, then your this output is going to give you the high voltage, and this is how the square waves are generated. Now, if we just go for the transfer characteristics or the hysteresis loop, just see what happens here is, this is your VLT and this is your V upper threshold voltage. This is V and this is your output was written for this, and here it is your characteristics between input voltage and the output voltage. Now what is being done is, when the value of the voltage is below VUT upper threshold voltage, your this output will remain at a minimum level. But as soon as it crosses your this upper threshold voltage, your this voltage is going to rise up to the magnitude that is defined by. So now what happens is, your this voltage has got risen up. Now again, when it is coming down below the lower threshold voltage, it will go to your that bare minimum constant level that was defined for your that Schmidt trigger. So now what will happen when your this voltage is getting to a low, your this value of the voltage will keep maintained at the same level. It will be maintained at the same level until and unless your this lower threshold voltage level has been reached. And as soon as this VLT has been reached, it is going to come down to its initial value. And if you just check out the curve, you are going to find that it is the same as is defined for your hysteresis for your BH curve. It is just similar to the BH curve. So that is why this is also called the hysteresis curve or the transfer characteristics between input voltage and the output voltage. So all these things define the parameters of your operational amplifier. Hopefully you have understood it. So the next lecture we are going to go for your analog instruments, the new chapter that we are going to start.